Hi, thanks for coming to my talk, especially this late in the conference. I'm Victor, I'm a principal developer at EG, and we've been playing with commercial property data in one way or another for 160 years, of course not digitally. We're not time travelers, just a company. But during this time we've realized that the way we do data models as an industry, and I'm not speaking specifically commercial property, I'm talking the tech industry in general, leaves a little bit to be desired. And the reason for this is that we tend to focus on the wrong things and the wrong trade-offs. So trying to be a part of the solution, of the problem, we're trying to explain now what it is that we mean by data modeling, what are the historical artifacts that we have used to do data modeling, and in the end, what are the problems we face that motivated us to look for something else. So before we start, we should really define what it is that we are talking about, and that is, what is a data model? So when we talk about data model in EG, we say that the data model is an abstract representation of any real-world domain. That means you have something real, so you have this conference and the attendees and the speakers, or you have a shipping company, so the stuff you are going to ship and the shipping lanes and so on and so forth. In our case, property transactions, agents, prices, etc. When you are modeling anything, you have to figure out three things. First of all is the structure. The structure is all about the entities you are working with and how they interconnect. Then there is operations. So how do you create things? How do you delete things? How do you modify things? And then there is rules. If you have an e-commerce website, which we'll get to in a minute, you want a user to be attached to an order unequivocally, for instance. So you have to model all those three things in order for you to be able to say that you modeled your domain correctly. But of course, everything starts with roughly the same shape, which is empty. This is all your universe, your domain universe. That is not everything in here, is just what you care about. Shipping, property data, banking, whatever it is that you work on, it's empty. So you can do anything you want with it. And the blank page is always very threatening, feels very threatening. We feel very small against it, so we want to find ways to actually have a repeatable way of modeling things against the blank page. And historically speaking, we've been using particular ways of doing this. And the first of these models, these models actually that actually was useful and left a mark, is the relational model. Dating from 1917, some prior work in the 60s, something in the 50s, depending on who you ask, I disagree, but doesn't matter. Cott published in 1970 the relational data model paper, in which he defines how you model data in a relational database, what we today call a relational database. The main idea is that you have your tables with your entities. It's based on relational algebra. That means there is relationships between things, and you model those relationships within the data. You have your relationships, one more column, and they link to something else. That leads to a worldview that is roughly this. Don't think about this as Venn diagrams or anything. This is just a way to represent what I'm talking about. So you have your orange entities, your blue entities, and your green entities, and they are related in the sense that they overlap a little bit. So you have information about how the blue connects to the green in the blue-green section. This is only possible because you have referential integrity, which will be important later. This is called foreshadowing. So referential integrity means that when you create something related to something else, that relationship is guaranteed to be good. And if that relationship goes away, you can cascade delete everything. So that helps you keep the system properties intact. Going to a more specific example, let's say you have an e-commerce website, your usual Magento or whatever the hell you are deploying in this case. You have your orders, your users, and your order items. You create an order that belongs to a user, that has a number of order items in that, and you have a set of operations as well. When a user produces a new order, the order includes the user ID in it. So that's how you create a new one. You create a new order with the user ID in it, and you create order lines related to that order. That is how you create that particular operation. There is also some rules. The user and the order have to be linked, the order item and the order have to be linked, and those things have to be valid. So for a word in this shape, this is a very good model. It's actually so good we have our own notation. This is a one-to-many nullable, that is a one-to-many non-nullable. We got very well versed in how to use this. And in fact, it was wildly successful. We used this for a few decades. In fact, we're still using it every single day. But every model starts very small and very easy to understand. And that's a problem. Every model starts very simple, so inherent complexity will eventually appear. And I'm not talking about complexities related to how you use it, your operations. I'm talking about complexity that is intrinsic to your space, to your problem space. If you are in shipping, there is many routes, they overlap, you have to take variants depending on what you're doing. If you're in banking, you have the complexities of the banking law. If you're in property, well, property is just very complex because the UK law is very, very thin. So any tool you imagine can be used, can be overused, and can be abused. And SQL databases were abused quite a bit. In fact, if all you have is a hammer, everything looks like a nail. And everything for us looked like a relational database. So we just kept using them. And our joins kept getting really, really interesting. If you worked for any period of time optimizing database queries coming out of any PHP code base, really, you will know what I'm talking about. They were massive and they were just ugly. So there was an industry-wide reaction to this. And I think the seminal work you can trace back to the beginning is the Big Table paper from Google. It's 2006, so in the early notices when this space started to get a bit busy. The idea was this. The relational model is very good if you have bank accounts and you have to guarantee transactional integrity. That's fantastic. It works very well. It's arguably the most successful model for that. But sometimes you do not. And sometimes your data is not shaped that way. Simply it's not. So in those cases, what you want is something else. And that's what led down the road to MongoDB, to Redis, to Elasticsearch, to VaultDB in the early days, and so on and so forth. All those databases. And of course, DynamoDB, which is a direct copy, inspiration, I don't know how to call it, of Bigtable. It's the same stuff. The idea here is that you model the universe in a way that is slightly different. You have your distinct pockets, and you model those pockets a bit more independently. The relationships are a bit more tenuous. We'll get to why in a minute. In fact, if you give names to this, we have, let's say we're modeling a company, we have engineers, lawyers, accountants. We try to be separate, we actively try to be separate, we don't want anything to do with each other, so we're good with this model. On top of that, let's go back to the e-commerce website. In reality, if you have a problem space, you can model that problem space in many, many different ways. And they are not all correct, and they are not all equally correct, but they can all work for you. So you can model the same reality in different ways. The reality is the same, the problem is the same, but you can choose different tools depending on the different trade-offs you want to focus on. For instance, you could say you have the green entity, that's separate, you have the blue entity, and the orange entity that is inside the blue one. We used to model this with a relationship in relational databases, just a relationship, or we just embedded the data making everything a lot wider, which created its own complexities. But maybe if it belongs inside, just put it inside, and these databases actually allow you to do that. Going back to the example originally, you have your users, your orders, and your order items. It doesn't really make sense for an order item to be outside of the order, because it will only ever belong to one order. You don't want to reuse them. It wouldn't make any sense. It would make editing a nightmare. So you can keep them inside. In MongoDB terms, this would be a subdocument. There's a subdocument of the order. It's all in one place. You don't want to join anything. You don't have to join anything. So you're good. And the user lives outside. Now, could anybody point out at the pretty obvious mistake in this model? What is the main issue we will face when working in this particular shape? What happens if you create a new order and the user never existed? It allows you to do it because there is no referential integrity, hence the foreshadowing earlier. But of course, it doesn't mean it's the Wild West and you just create data whenever you want, whenever you fancy, and just it doesn't matter and every data is dirty. You have to implement checks just somewhere else. That is one of the key things about NoSQL databases. They do not eliminate barriers, they just move them, and they move them towards the developer. You have to implement checks somewhere. If the database doesn't do it for you, well, you have to do it. It's on you. You have to guarantee your data is correct. That's your job, quite literally. So that is the trade-off here. So relational databases, they are pretty good at modeling relations. That's about it. They can, via joins, they can combine data together very well. But those joins can get very expensive. NoSQL databases, they remove joins. They allow you to model things a bit differently. You have to shift your thinking about how you model things. Some things become a lot easier. Some other things become a lot harder, and you have to implement a few checks yourself. That is a key trade-off. There is no free lunch anywhere, nothing. So you have to do something about it. If that's a trade-off that works for you, fantastic, go for it. We have, and it's good. If your model is actually more relational shaped, then you should probably consider something else. But of course, this is it's contrivedly small example. It doesn't really make a lot of sense because things tend to be a bit bigger. We said before that complexity starts appearing when you grow your models. In fact, some models look a bit like this. So you have combined relationships, you have 3 in one here and then half of 2 in there. It gets very, very messy. Now, you may think that I'm just being obtuse and I'm using an artificially contrived example. The problem is that this is actually my day job. This is actually what commercial property looks like. You have your buildings, which have the owner of the land sometimes, and then the source of the building, then you have some virtual freeholds, some people letting that, some people owning the land, some references to the addresses, and so on and so forth. So if you try to model this particular thing in SQL, your joins would get really spectacular in a bad way, not in a fun way. They will get massive, and they could get very, very slow, and optimizing these queries is going to be a nightmare. Trust me, I've tried. Then you can go NoSQL, and in NoSQL there is techniques to model this kind of thing. There is heavy denormalization. You keep copying things across. The problem is that if you have 2 copies, you have to keep track of 2 things. If you copy things 15 times, you have to keep track of things 15 times. You are almost guaranteed to be losing data at some point or another. So in these cases, you run across a problem, which is that the data model has to reflect reality. It has to, because that's what you're trying to model. Reality does not care about your model, does not care about your feelings. If your model sucks, it sucks. There's nothing you can do about it. And there is no silver bullets. If some database vendor comes and tells you, yes, this can model everything these other databases and more, most likely, no. Even more likely, they are not even aware of the problems. And even more likely, they're just trying to close the cell. So there is something fishy there. There is no tool that fixes everything. And sometimes, for some particular problems, you have to take a step back. So let's look at another piece of literature. Let's look at the graph traversal problem. This is a pattern, excuse me. This is a paper from 2010 from Neotechnology, which is now known as Neo4j. You can see them over there. Pretty nice guys. And it proposed something else. So instead of focusing on the relationships and the data, focus on the traversal of the graph to get to that data. This has its roots a few centuries ago. In fact, in 1736. The problem here was the following. This is Königsberg in Germany. And there is 2 main islands connected by a single bridge. And it's in the middle of a river. So you have land at the top, land at the bottom, 6 bridges. In total, 7 bridges. And people kept asking, okay, is it possible to go through all 7 bridges without repeating any single bridge once? So you go through 7 bridges, 1 time each, exactly. Now, Euler, who was a very prolific mathematician, figured out an alternative way to look at the problem, because it remained unsolved for quite a minute. So he thought, okay, why don't I just create graph theory and topology? And he did, because he was Euler and he could. And this is the way he viewed the problem. Now, if you put on your relational database hat, you could say, look, it's very easy. There is a bridge table, and there is a land table, and there is 1 bridge for 2 lands, so it's a one-to-many relationship. Pretty easy. And then you make 1,000 joins and figure out what the solution is. Well, you could. You can try, I wouldn't, but you can have fun. But in this case, the main insight that mathematical philosophy tells us we get here is not the solution. The solution is remarkably uninspiring. It's very simple, actually. It's depressingly simple. There is nothing to see there. The key insight wasn't that. It's that he modeled the problem with minimal abstraction. That is, the problem is not what this node is or what this path is. It's that there is certain connections in a certain shape in here. There is a certain topology involved in the problem. It doesn't matter what's in between the bridges or what a bridge is. This could be spaceships, and this could be a path, this could be cities, and this could be a logistics path. It doesn't matter. The issue is that there is a path and you have to solve for that path. That is the key here, because sometimes you have to model what's actually important. If you go back to the e-commerce case, an order is important. That's what you charge money for. In fact, the monetary amount is in there. There is the user model. It's important because you are shipping stuff to those users. The order lines, they have to add up to the order total, so the data is very, very important. In some other cases, like the bridges, I don't care about how long the bridge is, or how big the city is, or what is the material, or how old the city is. What I care about is the connection, because those connections actually can carry data. And sometimes that data is more important than the data in the nodes themselves. And to illustrate how we apply this in EG, we'll go through a little example. And this is, if you forgive me, this is the only case in which we'll talk about commercial property. So let's go through a few examples and see how we would model this in both relational and non-relational databases. This building is 99 Bishopsgate, where EG is based. We have this sort of reverse L-shaped structure. That's one building. It has 4 bodies, but it's just the one thing. And do you see that red outline around it? That is the freehold title. Without getting into the technicalities, that expresses who owns the land. So we have the building, which is the physical structure, and the land underneath it. And let's say you wanted to build a relationship between the land and the building. If you look just at this case, you would say, well, easy. If you consider this one building, it's a one-to-one. So one-to-one, pretty easy. That's the simplest case, fantastic. You could be in the same table, and in NoSQL, it doesn't matter. You embed one in the other or the other way around. It still works either way. So, as usual, when you have a theory like this, you want to look for a counterexample. And if we go right across the road to 100 Bishopsgate, you see one. The building is this blue mass again, and you see all these tiny green things. Each of those is a freehold title. That means these people, the company of leather sellers in London, they kept accruing property since 1444 when they were founded. And they kept adding more of these freehold titles to their collection. And they didn't really group them together because taxes are really, really expensive, particularly land taxes. So they just kept aggregating them, and eventually they let people build at top of that freehold. That means the one-to-one is not valid anymore. It has to be a one-to-many, one being the building, many being the titles. So, okay, and in a non-relational database, let's say Mongo, you could say, fine, the freehold titles are a sub-document of the building, and this is what you have in there. But again, we have to find a counterexample, because we are in this business to just be contrarian, not to be fun. So we have this. And if you look at this title here, you will see that a single freehold title has distinct buildings inside it. Therefore, it's not a one-to-one, it's not a one-to-many, now it's a many-to-one. So it has to be a many-to-many. But of course, many-to-many relationships are an anti-pattern of sorts, so you have to be super careful with them, because they are typically encoding something that you are not super good at. In this case, you will have this case with freehold titles. With leases, you will have the same case with owners. One building can have many owners on one owner, many buildings, so everything ends up being many-to-many, so your joins become exceedingly fun, in a bad way. So in some cases, you have to actually take a step back and say, okay, if you are studying how these things connect together and you want to study the property market holistically from a high level, does it matter what this title is and how it's written, or what is the size, or what this building is called? Or is it important how they relate to each other? So this freehold overlaps with these buildings, and these buildings with these freeholds and leaseholds, etc. Let's assume we try to model things with connections. And we say, whenever something is atop of something else, that's a connection. And we just let the model grow organically. We don't really impose any restrictions by hand. We just say, get the connections and explore what this looks like. You would end up with something similar to this. Maybe you cannot see very well. This is a connection here. There is a V connection there. So in blue, you have buildings. I remove the freeholds because they are a bit noisy. In red, you have addresses. So every building has a few addresses. Like 99 Bishopsgate can be 99 Bishopsgate, 101 Bishopsgate, 99-101 Bishopsgate, and 45 Old Broad Street, because London property is always super fun. So you have a few addresses, a few floors for the addresses as well, and you have leases, people leasing property. So you would have a bunch of addresses here, you have the building themselves, the actual structures, and the leaseholds inside them. And we just threw everything together. We just didn't really try to impose any rules. We said, focus on the connections. We see two things. One of them, we see that these 4 buildings on top and these 2, they are related to each other by use. These leaseholds, they are actually linking them because there is common use across both buildings. Same on top. And all these addresses refer to the same building, so we create those clusters. Second, inside, there is a very clear decision boundary between those 2 subgraphs. And that is the key aspect. This happens to be a building, that happens to be an actual building. And the relationships emerged instead of being forced by us. And that is the insight here. Abstraction can really get in the way and obscure what you're trying to do. You should abstract just enough that the properties emerge and surface. In this case, we approached everything with the naivety of a child, and we thought, let's put everything together, see what happens. And the properties were pretty evident to us once we plot the graphs. In other words, you should only abstract what you understand. We understand the market very well, we know the interactions, so our abstractions let the data shine through the model. And that is how we solve this particular problem. So I'm not saying here that graph databases are the ultimate solution for everything. That's Neo4j, not us. Different stand. What we're seeing here is this. People tend to model in a way that is very familiar to them. So if you are really into relational databases and you are a SQL consultant, you tend to model things SQL. All relational, all relationships, all joins, all day, every day. Maybe you denormalize a few things, you use canonical models of higher order. Okay, fine, fantastic. But it doesn't solve all the problems. Maybe you are really into NoSQL. You hate SQL with a passion. You think joins are what Satan uses to trick us into using SQL, relational databases. You are really into MongoDB and everything is a document. Some problems do not fit that way of thinking about things. And some other things don't fit either of those two. And also some things don't fit this either. So every time you come across a new problem, you cannot really shoehorn it into something. You have to first understand the problem, understand what it is that you are modeling, and then the properties, you abstract just enough that the properties start emerging, and then you can make a decision. For us, it took us 5 years to realize document databases were not good, and about a year to realize SQL was not fantastic either, that a graph was the solution. In practice, database vendors will keep pushing these fixes, all the problems, and then some. In practice, no. Everything has its use. Any tool can be misused. Any tool can be abused. So you should model the reality you see and the reality you understand, not your database's vendor's idea of it. And again, novel ideas need novel tools, and that's what you should focus on, understanding what you have in front of you. And that's it. Thank you. Now, does anybody have any questions?
Hi. So thanks for the presentation. As you said in the presentation, reality doesn't care about our tooling, and that way reality doesn't have to care that it fits in one model. It could be relational NoSQL or graph model. So what happens when reality fits in multiple models?
Yeah. Well, you choose whatever it is that you feel comfortable with, to be honest. Or there is another way, a bit more subtle way to answer this question. I was just being deliberately obtuse. The answer there is your model itself and then what you want to build on top of it. So if you want to build something that is that lends itself very well to be in a search engine, that's probably Elasticsearch. If you are building something that is heavily transactional, SQL database is a good choice. Then if they are on the same footing, pick one, doesn't matter. I have no preference, I don't care.
Thank you.
Any more questions? Good, then that's it. Thank you very much.